Hello, welcome to the dSPACE Learning Connection. My name is Alexander Trapp and I am a product manager for DARTS at dSPACE. Today I want to answer the question how to validate radars with DARTS. And to do this, I will first introduce sensor testing at dSPACE in general, then go into detail on over-the-air radar testing, which is exactly what we are doing with DARTS. Then I will show the DARTS portfolio and shine some light on what can be done with which DARTS. After that, we will focus on the use case target separation, tell you how the new DARTS-9040GT can help you when you are faced with this challenging use case. And at last, I will give you a short demonstration on how different separation tests can be performed with this unit. So let's start by taking a look at how sensors can be tested. If you look at the different components of a sensor and how the data is handed down the processing chain, you can immediately see at which points a simulator can interface with the sensor. The most technology-independent option is to generate object data, which you would expect of a sensor, and inject that immediately into the vehicle network. That is option 1. Or insert it before the application logic inside the sensor, which is option 2. While this is a good way to test ADAS control units, this is of course not testing the sensor itself. The next alternative is to generate the raw sensor data in a physics-based simulation, like a ray tracer, and inject this somewhere behind the front end. This is much more closely related to which sensor is actually tested, because the raw data of a camera or LiDAR will look very different. Making this work requires an interface to the sensor and in-depth information about the internal processing to prepare realistic data. In return, this technique allows a much larger test coverage within the sensor when compared to the previous option. The last option is a simulation over the air. This technique tests the entire real sensor, including its signal transmission and reception path. Since the air interface is the same for all sensors, just the real surrounding, nothing needs to be known about internal processing, and the sensor can be treated as a black box. Which of these options is chosen for validation depends on which information is available to the user, what components shall be covered by the test, and how complex the test scenarios shall be. Today, I will focus on over-the-air testing of radar sensors. This is the method where DARTS is used standalone or with a radar test bench. But to give you a little bit of context, I will also shortly touch the other sensor simulation methods. The ResBus simulation is used for the previous option 1 and 2. The whole communication of the sensor ECU is simulated and injected into the vehicle network with the bus manager. There may not even be a sensor involved. This is useful to test if a sensor, like the simulated one, would integrate well with the system. Sensor simulation and data injection are both options 3, but with the twist that the sensor simulation test is done purely virtual to test the sensor software and the modeled sensor processing to develop the algorithm without the need for hardware. For data injection into a real piece of sensor hardware, the Environmental Sensor Interface Unit, EASY unit, is used to inject the simulated data with the necessary bandwidth over a given interface into the sensor to test all the following processing steps. And with over-the-air testing, of course, we simulate the real sensor return. May it be a video screen for cameras or radar echoes with DARTS. I will go into detail on the different use cases for DARTS later on. I already said that all of these methods complement each other, but they can also be directly combined. This is an example for a comprehensive ADAS AD simulation using different tools from dSPACE. There is different over-the-air test solutions for radar, camera and ultrasonic, as well as the possibility to inject data with the EASY unit. Together with GNSS simulation and different V2X solutions, the complete vehicle environment for a central ADAS ECU can be simulated. All of this is synchronized with the traffic and vehicle simulation that is running on our real-time PCs Galaxio. And to close the loop, the feedback of the ADAS ECU can again be fed back into the simulation to include the actions of the system under test in real time. So much for the general sensor testing. Let's now concentrate on over-the-air radar testing. This is the working principle of the dSPACE automotive radar test system, shortly DARTS. At first, the radar transmits its signal, and this is then received by DARTS and converted from the high radio frequency to a lower intermediate frequency. This can then be routed to the DARTS base unit by a cable. Inside the base unit, the signal is enriched with one or more simulated targets. The target parameters speed, distance, and size are programmed inside the DARTS and can be controlled to fit the test scenario. After processing, the signal is again routed to a converter. There it is converted into the radio frequency of the radar and sent back. The sensor receives this modified signal and extracts the object information that we added. And this principle applies to all DARTS and radar target simulators. Here you can see how this may look in hardware. The golden matchbox-sized box is a converter, and the silver box to the right is a DARTS base unit. Note that the working principle does not require any measurement or analysis of the radar signal. It is routed through the DARTS and processed on the fly. We do not have the time to do any analytics because any processing delay will cause additional simulated distance with the speed of light. This is why we call DARTS an agnostic target simulator. We do not need to know anything about the radar signal and modulation. This DARTS can now be used within one of our radar test benches. Due to the extremely small converters, it is possible to stack multiple converter pairs very closely and move them with very high precision and dynamic. This mechanical movement is necessary because one important target parameter is still missing, the angle of incidence. This value is decided by the physical location of the DARTS front end with respect to the radar under test. Now, what can we do with this? Turns out quite a lot due to the complete coverage of the whole radar sensor and all subsequent processing. It can be used to test the specifications of single radar sensors as components like detection accuracy or object separation. It is used to qualify the impact of the environment of the radar sensor and everything that is within the signal path, like radomes or bumpers. But it can also be used to test more than one sensor. It can test the response of an ADAS function to different scenarios, such as NCAP scenarios, and make sure that the response of every system up to the whole car is working as intended in every given scenario. Due to this high flexibility of the tool, DARTS is used in all the different stages of radar development, validation, and production. It is used in chip testing, where a reference grade simulated target is appreciated. The Tier 1s use DARTS heavily during development and production for many use cases. It is used along each step of integration, first into ADAS functions and then into whole vehicles. At the end of the life cycle, DARTS can also be used for periodical technical inspection to test that all ADAS functions are still working in the field, even if a car has been running on the street for multiple years. Here are some public examples of companies that use DARTS to test and validate radar sensors. As you can see, there are a lot of different applications for a radar target simulator, such as DARTS, and a lot of different market segments with different requirements to such a tool. This is why we have a broad portfolio of different target simulators that are specialized to specific use cases. We have a target simulator that provides targets at very long ranges, up to 1 kilometer, or another one for very short ranges, down to 60 centimeters. There is also a system that combines these two to allow full range testing from very close to very large away. Then there is a target simulator that is used specifically in environments that require a rugged, low-cost tool. And our most recent system, the DARTS-9040G, was developed specifically to test next-generation radars that have a higher processing bandwidth and higher sensitivity to any kind of simulation artifacts. Just now, we are releasing an expanded version that provides two simultaneous targets, either from one angle or from two different angles. Later on, I will explain why and when this is an important addition. To answer this, there are two basic questions. How much bandwidth does the radar under test use? And what are the requirements on the simulated range and the number of targets? When this is known, the suitable darts can be chosen, and we can proceed to some secondary questions, which are: do we need even more targets? Due to the working principle of darts, it is no problem to combine multiple systems in one simulation. Darts can be added and removed from test systems very flexibly and with minimal effort. Next question is an angle simulation required? Then we use one of our radar test benches that use mechanical movement of the radar sensor and DARTS front ends to control the angle of arrival of the generated targets. The next important question is the use case a scenario-based test in real time, maybe even in synchronization with other sensors? Then we control the darts from a real-time PC, such as our Galaxio system. As you saw before, these systems are very powerful and can be modularly expanded to include more radars, other sensors, or generally components that should be covered by a test. And the last question is, do we want to do some additional measurements, such as the emitted power of the radar sensor or the occupied bandwidth? In that case, we can use the IF sample ports on the darts to attach measurement equipment that works in the single-digit gigahertz range instead of expensive radio frequency equipment. And if all of this is done, you have configured the optimal system for your test requirements. Now, I think it is clear that the different ranges and number of targets mean for possible scenarios to be simulated. But why is the bandwidth of the used radar so important? The answer is because bandwidth decides the range resolution. While systems that only use the narrow long-range radar band have a theoretical resolution limit of 15 centimeters, radar sensors working in the short-range radar band can go down to 3.75 centimeters of range resolution at 4 gigahertz. Even a radar that is combining both bands for a modulation bandwidth of 5 gigahertz is limited to 3 centimeters of range resolution. This is why the questions for the radar bandwidth is so important, because the test system must itself be able to handle the high bandwidth and have a higher range resolution than the radar under test to cover all test cases. And this is exactly what our high bandwidth radar target simulators do and why there is such a hard split between the systems when it comes to the bandwidth. Now, let us dive a little deeper into a specific radar test case, target separation. This is a collection of test cases where radar target simulators are used during the life cycle of a radar. Depending on the application of the radar chips and sensors, a collection of these tests has to be performed. In the previous slides, we have learned that the range resolution is a key specification of a radar sensor. High efforts are spent by Tier 2s and Tier 1s to lower this resolution for improved performance in ADAS and AD. Together with the angular and speed resolution, as well as higher sensitivity and accuracy in general, this is a mark of next generation radars, so-called 4D imaging radars. These specifications are decisive for the performance in ADAS and AD, so they must be tested and validated thoroughly. To reach the intended accuracy, the radar has to be calibrated properly. The higher sensitivity that is used to detect even the smallest targets, such as a metal can on the road, makes ghost targets more likely. To prevent these ghost targets, even the smallest spurious or artifact of radar processing must be found and assessed. And to validate that the resolution of the radar matches its design goal, the separation capability must be tested in every dimension: range, speed, azimuth angle, and elevation angle. These separation tests are especially challenging because they require two simulated targets, which should be identical in every parameter except the one that is tested. Now, let's shortly go through the different separation tests. The range separation test determines the range resolution of the radar sensor. The basic question that has to be answered with each test is, at which minimum range from target to target can the target still be resolved by the sensor? This has to be tested for a range of different target speeds, target sizes, and also over the whole field of view of the radar sensor. This is to make sure that the specification hold in every case. In more advanced tests, the RCS values, so the sizes of the targets, may be chosen differently to find out how the resolution versus when one target is very large and the other is very small. In reality, this would be the case if, for example, a pedestrian would walk next to a parked car. I think it is obvious that it is important to know how well a radar sensor may perceive the pedestrian in this case. Next is the Doppler separation test. This is basically the same as the range separation test, only this time we keep the ranges the same and only change the speed of the simulated target to determine the speed resolution. And at last, there is the angle separation test. This test has to be performed both for azimuth angle and for the elevation angle resolution. These are typically very different for automotive radars that have a much higher resolution in the azimuth angle. In some cases, only the newest generation of radar sensors start to measure the elevation angle at all. The relative angle between the targets is not controlled electronically within the darts, but by moving the front ends from which the targets are simulated mechanically. And this is an important difference between the previous separation tests in range and Doppler and the angle separation tests. For the first two, we need two targets from one front end so that the angle of incidence of both targets is identical. And for the last two, we need two front ends that simulate otherwise very similar targets. If these requirements are broken, we cannot trust the result of our test. We cannot be sure if the targets are separated due to the range resolution, for example, or if a slightly different angle of incidence leads us to think that the range resolution of the radar is lower than it actually is. Up to now, the solution for this test was to use two DARTS-9040G. This target simulator was released in 2020 to address 4D imaging radars with a high bandwidth covering the whole automotive radar band with 5 GHz instantaneously and a range resolution below the limit of 3 centimeters. Additionally, the very precise simulation and lack of ghost targets make this the optimum choice to test next generation automotive radars. But while all separation tests are possible with this setup, it is quite complex, especially changing the front-end configuration from 2 separate front ends to 1 front end united for both DARTS-9040G is an error-prone process that tends to disrupt the alignment of a setup. This gap is now closed with the DARTS-9040GT. The DARTS-9040GT has all the advantages of the DARTS-9040G. The difference is that it simulates 2 independent targets on its own. These targets can be simulated from 1 front end or from 2 separate front ends on demand. Only with a command in the software, the front end configuration changes without any changes to the hardware. No changing cables, no screws, and no hardware changes at all. There is no need for anyone to even be in the room. Tests can be done fully automated or remotely. This ensures that one device can be used to satisfy all separation use cases, in addition to all the other radar testing applications that are mentioned previously. When compared to 2 DARTS-9040G, this is much easier to operate and less expensive. And it is available next month. And this is what it looks like. Not much has changed. It has become a bit larger, and of course it now supports up to 4 converters to form 2 front ends. In addition, we have used the opportunity to further improve the phase noise values and increase the maximum system gain to enable the simulation of even larger targets at close range. Of course, all the firmware features that are supported for the DARTS-9040G are also available for this new unit. Let me shortly give you an explanation what all of these features actually mean in reality. At first, the interframe switching. This, what you see here, is a typical FMCW radar frame that consists of portions where the radar actively sends out chirps separated by frame pauses between 2 different frames. The radar target simulator typically switches all the target parameters whenever they are set by the users. This is because there is no analysis done in the radar target simulator at all, because it is agnostic. But this can become problematic because an abrupt change in the simulated range leads to a phase discontinuity in the signal. This is no problem if there is no signal, but if this happens just during a chirp, this can lead to artifacts in further processing inside the radar sensor. With interframe switching, DARTS automatically detects frame pauses and only changes the simulated range during such pauses to prevent this kind of artifact. Second, the gain flatness compensation. The wide band gain of radar target simulators and generally of all systems working at wide band in these frequencies is not perfectly flat. This can become problematic when low bandwidth radars are used with specific center frequencies. In this example here, 77 GHz or 81 GHz would be problematic. In this case, the actually simulated RCS value of the DARTS may deviate by multiple dB from the set value. However, to compensate for this, the individual gain curve of every DARTS is measured during calibration and can be used to shift the whole gain curve to compensate this deviation when this feature is activated. Third, the self-test. DARTS is used for very sensitive applications. For example, calibration of radar sensors during production. It is important to make sure that DARTS is always working within specifications. To do this, DARTS can diagnose its internal signal chain for deviations from a factory calibration and for internal consistency. This function can be triggered by the web interface or with the API and logged. For example, before and after every test in production. And with this, it can be documented that DARTS is providing a stable simulation that is repeatable and reliable. And at last, MicroDoppler. In addition to the target parameters that were discussed previously, range, speed, RCS and angle, DARTS targets can also be enhanced with a MicroDoppler signature for vital sign simulation. On the left you can see one possible model for breathing and heartbeat that is then imprinted on a simulated target. On the right is a human vital sign measurement demo from Texas Instruments that is extracting exactly the data we have added. This feature can be used to test radar sensors that detect vital signs, for example, for in-cabin applications. Before I come to the conclusion, let me show you a short demonstration of separation testing with DARTS-9040GT. Here you can see a simple example how the DARTS-9040GT can be used to perform separation tests with a radar sensor. In the top video, you will see from left to right the darts, the front ends on a holder, a small anechoic tumble, and to the right the radar sensor. You will be able to see how I physically change the two front ends that are positioned right next to each other on a guiding rail. On the bottom left window, you will be able to see the changes I make in the DARTS web interface. And on the right are the detections of the radar sensor, plotted first over range and the azimuth angle. And in the second plot, there is the Doppler speed over the azimuth angle. The front ends start with a larger distance from each other. So you can see both targets at the same range, slightly above 50 meters, the same speed of 18 kilometers per hour or 5 meters per second, and slightly different azimuth angle. I will now start by pushing the front ends together. And as you can see, at some point, one of the detections vanishes, which shows that the sensor is not separating the targets anymore. And with this, we have found the azimuth angle resolution of the radar sensor in this sensor configuration. And now, when I pull the front ends apart again, we expect that the targets will again be separated by the sensor. And this is the case. But this is of course only one separation test. Next, I will show the range separation test. But now we have a problem with the two front ends in this setup. We can move them as close together as possible. This is now beneath the resolution limit again. But when I now change the speed slightly to make it easier to resolve the targets, we can see that there still is a detectable difference in azimuth angle between two targets. And this is exactly what would invalidate a range separation test in this configuration. As discussed before, it is necessary to simulate both targets from one and the same angle, and to do that, I can now just change the front-end configuration in my DARTS software. As you can see, we are now simulating two targets with exactly the same azimuth and angle and Doppler, and only a difference in the range. And now we can do basically the same as before. By decreasing the range of the farther away target at a specific point, the two detections merge into one single detection. This is then the range resolution of the radar sensor. If you would like to see how this test would work with your radar, we offer demonstrations and also evaluations on site at your place as well as remotely. Now to shortly summarize this learning connection. I've shown you a small overview on the different solutions that dSPACE has to test automotive sensors. One very powerful tool to test radar sensors is DARTS. Due to the agnostic working principle and its flexibility, DARTS is applied for a lot of different use cases over the whole automotive value chain. Separation tests are an important test case category that up to now lacked a tool to cover it completely. With the DARTS-9040GT, there is now a DARTS product that is ready for next generation radars and covers all separation tests in a comfortable and reliable way. Thank you for listening. If you have any questions, I'm happy to answer them in the Q&A session, which is following right now. And if you come up with questions later on or are interested to learn more, please do not hesitate to contact me. Thank you very much.